Welcome to today's in-depth technical analysis. Let's jump right in. Today, we're tearing down one of the most hardcore, high-stakes areas of hybrid drive systems, engine and dual motor coordination failure. In complex architectures like eCVTs, we're dealing with an ASIL D functional safety system, where the engine, drive motor, and generator are mechanically and electrically joined at the hip. If this goes wrong, it goes catastrophically wrong. Today, we're going to break down exactly how this system survives extreme conditions and how engineers build an absolutely airtight defense network. Think of it like a world-class orchestra, where the engine and motors are your lead performers. When making a highly dynamic mode switch, like instantly snapping from pure EV to hybrid, or surviving a sudden engine pull-up, these three have to sync up their torque and speed in a matter of microseconds. So what happens if they lose that coordination? If anyone is off by just a fraction of a millisecond, the whole powertrain crashes into destructive torsional resonance. Or you get these deadly DC bus voltage surges that can instantly kill the system. To stop this, we rely on a massive defense-in-depth strategy. We've got a 5-step roadmap for this explainer today. First, fault root cause analysis. Second, software and hardware co-diagnostics. Third, DFMEA key design preventions. Fourth, PFMEA key process controls. And finally, DVPNR production validation. Let's kick things off with Section 1, Fault Root Cause Analysis, focusing on the physical dimensions of these failures.
To solve the problem, we have to play forensic engineer. There are 4 major physical failure modes here. First up, intense torsional impacts from engine combustion. If your active damping control lags by more than 90 degrees, that negative feedback flips into positive feedback, literally tearing the drivetrain apart with resonance. Second, during cold cranks or heavy loads, massive motor currents push the magnetic circuit into deep saturation, completely throwing off your field-oriented control, or FOC model. Third, when SiC MOSFETs switch at high speeds, they spit out transients over 10,000 volts per microsecond. That crazy common mode noise totally scrambles low-voltage communications.
But honestly, the most mind-blowing one is this counterintuitive mechanical failure, fretting corrosion. You've got a multi-ton vehicle brought to its knees by just 10 microns of wear. Random 100 to 1000 Hz engine vibrations travel down to the low-voltage harness, causing microscopic slippage at the terminals. It's like invisible sandpaper, scraping away the tin plating, forming insulated oxidized debris. Your resistance suddenly spikes from under 5 milliohms to over 100. That causes microsecond signal drops, completely blinding the controller's resolver signal.
Moving to Section 2, Software and Hardware Co-diagnostics. This is how we build our safety defense net. Knowing how brutal these physical failures are, we have to build a lightning-fast immune system to intercept errors before the car unexpectedly accelerates. Step 1 is a dynamic power balance check, constantly comparing mechanical output power against DC electrical power in real time. Step 2 is a speed plausibility check, cross-referencing hardware decoded speed, software estimated speed, and actual wheel speed to catch any rogue signals. And Step 3 is our absolute baseline, an independent Dewar-Checker dual-core lockstep architecture. The craziest part about this immune system is the strict time constraints. In that first power balance check, if the mechanical and electrical power differ by more than 15% for just 15 milliseconds, guys, 15 milliseconds is literally less than the blink of an eye, the system instantly flags a P0A7F coordination failure. It has absolutely zero tolerance. And at the hardware level, it gets even more extreme. Once the safety checker core figures out the main core's command will cause a massive DC power surge, it has less than 100 microseconds to react. Less than 100 microseconds. It has to instantly kill the PWM drive and shut down the power output to avert a total disaster. But just killing the drive isn't a one-size-fits-all fix. Physics dictates different fallback strategies based on your speed. If you're at high speeds, say over 7,200 RPM, the motor is generating massive back EMF. If you just cut the power, that high voltage will instantly fry the inverter. So the system uses a stepwise active short circuit to safely clamp the voltage below 720 volts. But if a fault happens at low speeds, under 2000 RPM, it triggers active open circuit, letting the motor freewheel. Why? Because suddenly braking electromagnetically at low speeds could lock up the wheels, causing you to lose total control of the car on the highway.
Moving right along to Section 3. DFMEA Key Design Preventions. Let's see how we inherently design out these vulnerabilities.
This is our vaccine.
To fix the resonance, we inject virtual Kalman shaft observers for active damping, which physically knocks down torsional resonance by over 20 decibels. For software stability, we use a hardware-protected lock-free double buffering IPC architecture across the cores, ensuring data never tears. We also bake in a high-precision 2D LUT for inductance saturation mapping to keep torque errors under 3% even at peak loads. And to solve that annoying fretting corrosion we talked about, we literally just use gold. We mandate 100% gold-plated terminals for low-voltage safety signals to physically block that oxidation path.
Section 4, PFMEA, Key Process Controls. Basically, foolproofing the manufacturing side, because even perfect designs can fail if assembled poorly.
On the factory floor, human variation is zero tolerance. Traditional pneumatic wrenches are totally banned for high-voltage bus bars. We use precision servo closed-loop tightening to prevent any loose connections that could cause thermal runaway. At the end of the line, the system does automated rotor zero position learning. If that data doesn't perfectly match the MES cloud database, it physically locks the product. No shipment. Plus, 100% of critical SMT solder joints go through 3D automated X-ray inspection.
Why X-rays? Because the voiding rate for all SMT solder pads is strictly capped at or below 5%. We need these joints to be incredibly tough to survive daily, brutal engine vibrations without forming microscopic fatigue cracks that could drop a signal.
Finally, Section 5, DVPR Production Validation, the ultimate stress tests.
These are the clinical trials before this thing ever hits the road. The system has to endure 1,000 hours of combined thermal and vibration aging, and those gold-plated terminals can't increase their resistance by more than 1.2 milliohms. Against brutal 10 kilovolt per microsecond electromagnetic interference, there can be absolutely zero frame loss. And during HIL fault injections, where we intentionally try to break it, the system must diagnose and safely resolve the fault in under 60 milliseconds, keeping that bus voltage strictly under 720 volt.
So, wrapping this up, from blocking physical failures to microsecond dual-core lockstep defenses, this is what it takes to build an ASIL D hybrid system. I'll leave all the engineers watching with a challenge. Are you ready to leverage Python co-simulation tools to precisely optimize your active damping phase and safety ramp-down rates? When you're on the bleeding edge of coordination failure, squeezing out just one more microsecond of safety margin could literally mean life or death for the system. I hope this deep dive sparked some ideas for your next design.